So it is a pleasure to present Guillermo Mantilla Soler from the Universidad Konrad Lorenz and Aalto University. So he will speak about density questions on arithmetic equivalence.
Thank you so much for the opportunity to talk and for the invitation. I have to just be completely honest. This is more like an algebraic number theory talk. We sort of archaic Galois representations apply to algebraic number theory. So please not be offended if my use of Galois representation is not up to your standards. Anyhow, so I'll talk about something that I really like. I like to talk about number fields and finding invariants of number fields, things that to classify them, and not only any kind of invariants, but invariants that people usually find to be fun. I don't know what exactly that means, but that's what I like. So one that I really like is the Dedekind zeta function for a number field. So there's this definition which is called arithmetic equivalence. We say that two number fields are arithmetically equivalent if their Dedekind zeta functions coincide. That means that basically that means that if you want to count the number of ideals of a given norm in one field, that is exactly the same as the number of ideals of a given the same norm in the other field. This is sort of a what happened. This is something about sort of the result of Dirichlet series. If you have two Dirichlet series that converge in certain half plane, then they are the same if and only if the coefficients are the same. And here you can say even a little bit more. You could say that you only need to check what happened with the coefficients that are prime powers. Okay. Now, the first claim again is something about Dirichlet series, but here you can do it by hand. So if you have the two Dedekind zeta functions, and you want to say, okay, when are they the same? Then you just have to compare the coefficients. The first coefficient, the A1, is 1 for both of them because there's only one ideal of norm 1. And then inductively, and uses the convergence that you have, you could discover that the other coefficients are the same as it is explained on the slide. Now, the fact that you only need to check the coefficients that are prime powers, it is just a restatement of this, that the function that sends n to the numbers of ideals in the number field of norm n is a multiplicative function. That fact is sort of an arithmetic fact about the number field, and that's saying that the ring of integers is a residually finite Dedekind domain. Of course, you could restate that fact in terms of just the function, and that's basically just telling you that you have the Euler product like that. So there's three restatements about the function is multiplicative, residually finite Dedekind domain, of you have the Euler product of your function are essentially the same. Therefore, I repeat it again, if you need to check the two number fields have the same zeta function, you only need to check that they have the same number of primes of a number of ideals of a given norm, which is a prime power. Now, so the interesting question is, okay, what information can be obtained from the Dedekind zeta function of a number field? Besides being sort of a nice tool in arithmetic, can we tell anything very rich about your number field? Maybe you can have the whole information about your number field just in terms of the zeta function. And then, so I remind you, sort of, the first sort of kind of a striking result that you learn as an undergrad or maybe early grad student about the Dedekind zeta function is the class number formula, right? The Dedekind zeta function, it is a function that has a pole at s equals 1 of order 1, and the residue of that pole combines a lot of arithmetic invariants of the number field. Among those, as you know, so my notation should be clear. So the number of real embeddings, the number of pairs of complex embeddings, H is the class number, R, capital R is the regulator, D is the discriminant, W sub K is the torsion, the order of the torsion subgroup of the unit group. So there you have that formula over there. And then you also have something that I call the class number formula part 2, which says that not only that, but that function has a 0 of order that quantity, R sub K plus Sk minus 1 at S equals 0. And then you have this limit over here. Now, if you observe these two things, this is already telling us some information about the Dedekind zeta function, right? Sort of obvious information comes from this formula. For example, a very, very easy one is that the zeta function tells you the isomorphism class of the unit group up to torsion. That's sort of a very stupid statement. What I'm just saying, that's sort of a restatement of the rank of the unit group is this quantity over here. Therefore, the zeta function tells you that because that's the order of the zero. But also, will tell you a little bit more. If you take the quotient of these two numbers, right, this whole thing over here and this whole thing over here, what you get would be sort of a rational, no, not a rational, algebraic number times a power of pi. Okay, so and the power would be as k. Therefore, if two number fields have the same Dedekind zeta function, then by comparing these two ratios, you could argue that they will have the same number of complex embeddings, right? Because pi is transcendental and these other things are algebraic. Now, therefore, since you already have this number over here and you have sk, then therefore you have r sub k. So from this simple observation, you have the Dedekind zeta function characterizes the signature, characterizes the degree, and a little harder, but you could do it, and is you have to do a lot of like basic complex analysis, is you could check that you also will have the absolute value of the discriminant. This is coming from the, what is it? The analytic extension formula. You have to play a little with it. And then that's sort of how the first people who work with this were able to find all these sort of results. In playing it in the same way that I'm telling you, just sort of the analytic part of the formula. And therefore you can actually have a little more of the information. And those guys partly discovered that if two number fields have the same zeta function, they will have the same degree, the same signature, the same discriminant, right? As I explained to you, you will have the same absolute value of the discriminant, but since you have the signature, you know the discriminant. The ones that are a little bit more complicated, but not that much, and I'll explain in a second sort of what is the idea they're coming from, are items 4 and 5. So they will have the same, actually number 5 is a little more complicated, number 4 is a little easy. I didn't explain, but you could have done it since from the previous slides. But those are coming from certain group theoretical characterization. But if you know, for example, number 5, that they have the same Galois core, so that's the maximal Galois extension inside of the field. In particular, you know that they will have the maximal abelian extension. And if you know they have the maximal abelian extension, you will have the maximal, so you will know that the roots of unity in both fields are the same. Therefore, you have this quality over here. And by the rank, you know that the unit groups are isomorphic. And therefore, what you have remaining is, in the last part of the class number formula, is that these two numbers are equal. Now, one natural question to ask is, okay, now we have class number times regularity. Can we separate these two numbers? And the answer is no. Perlis and Bartlett-Smith in the 90s, they actually gave examples of number fields that have the same zeta function, but different regulators or different class numbers. So these two guys cannot be separated. So they just come together in here, okay? So now, one thing that this item 3 give us is that number fields that have the same zeta, Dedekind zeta function, there are not that many, in the sense that there are only finally many, right? Why? Because the discriminant is implied by the Dedekind zeta function. Therefore, you have that. Well, the natural question is, okay, but are there, maybe there is only one. Maybe the Dedekind zeta function is also a complete invariant, in the sense that two number fields having the same Dedekind function would be the same. The answer is, probably study these a little bit more. And sort of the idea is, first, it was just a combinatorial point, and then so just I give you a little definition. Given a prime, define the arithmetic type of a prime in a number field, as you take the residue degrees of the inertia degrees and you put them on a tuple, and you put it in an ascending order, so you just keep certain order, and you call that the arithmetic type. Okay, now because of the Euler product, you have this sort of equality. The Dedekind zeta function over here is equal to this product over here. What you do is you take the product over the maximal ideals and you distribute for every rational prime each piece. Now comparing for each little p prime, the right hand side here, when the left hand side here, okay, you will have sort of this combinatorial identity over there. Now the point of this combinatorial identity, we don't have to break it down, but it's sort of believable that the knowledge of the FIs will give you the knowledge of the AP to the M numbers and vice versa. You have to do a little basic combinatorics and you can do it. Therefore, it's sort of believable that the Dedekind zeta function is completely determined by the arithmetic types. And that's sort of the main theorem of arithmetic equivalence that Perlis proved. And it is in the 70s, he proved the following three things are equivalent. The functions are the same. The arithmetic types are the same for almost all prime. That means for density 1 set of primes. And certain groups are quasi-conjugated. What do I mean by certain groups? You take any, here I just wrote the compositum of the Galois closures of K and L, but you can take any Galois number field that contains K and L. Take anything you like. I'll take the Galois group generated by this field, and now take the corresponding subgroups given by the field K and by the field L. We call those guys arithmetic quasi-conjugated if for any conjugacy class in the group G, when you count the numbers of the conjugacy class in the group H1, that is exactly the same as the number of conjugacy class in the group H2. That is sort of related with the very famous problem about isospectrality of Riemannian manifolds. Okay, so I won't talk about it, but it's a very classic fact that this is related to the fact of finding spectral Riemannian manifolds that are not isometric. Okay, it's the notion of quasi-conjugation. And here I sort of put the graphic display of what I'm saying. You take the extension N over Q, this is the Galois group, and I said that these two subgroups are quasi-conjugated, the groups corresponding to K and L, if when I intersect conjugacy classes of G with H1, I have the same number with H2. Now that is going to be equivalent to the fact of the arithmetic type. Basically, the idea is to do a double coset of the group G by the composition group and the group H1, and then you can count and you can check by Frobenius density theorem that happens with the conjugacy class. Okay. Now, what is the power of these things over here? So, for example, the power would be that now we have sort of group theoretic way to detect when two number fields have the same Dedekind zeta function. I mean, it's kind of hard if I tell you two number fields and I give you the two functions. How can you check if they're equal or not? It will be a little hard. But with this group theoretical condition, you can do things. So, for example, the first thing that you could do is the following. So definition, a number field is called solitary. This is the definition of Perlis. If the zeta function determines the isomorphism class of the field. Okay. Now, Perlis was able to prove using this group theoretical categorization that if the degree of the number field is less than or equal than 6, or if the number field is an Sn number field or An number field, then the number fields are solitary. The whole point of this is that the group theoretical condition, the Sn is a group that does not have quasi-conjugated groups that are not conjugated. The same happens for An, and the same happens with any number field of degree less than or equal than 6, and the Galois closures. The groups are not that complicated. Now, something that might not seem that relevant over here, but I will explain later why, and that's how I got sort of interested in this, is number fields with fundamental discriminant are going to be solitary. This gave me a heuristic to find this theorem. I was looking for number fields with fundamental discriminant. They are related with some other invariant that we're studying, and then I come to these things with zeta functions. So this sort of gave me the idea that I was in the right path. Now, so here up to 6, we have this theorem over here of Perlis. An interesting question is what happened at 7. Now, it turns out that the simple group of order 168, it has two subgroups isomorphic to S4, two groups of order 24 inside that are quasi-conjugated, but they are not conjugated. Okay. Now, we have this group theoretic condition. If we were able to realize this is a Galois group over Q, then we will be able to construct two number fields that are of degree 7 that have the same zeta function. Why is that? Because this PSL2 F7, so I'll come back to my previous slide, these would be the G, right? Now I have here in subgroup of order 24, subgroup of order 24, then here index 7. These two guys will be quasi-conjugated by Perlis's theorem. They will have the same zeta function, but since they are not conjugated, that's something that we will have to have from the group, then they are not isomorphic. Okay, and then a lot of people just there are a lot of tables of realizing this group as a Galois group, so you can actually construct septic number fields with the same zeta function in a very explicit way. Okay, so you could have septic number fields with that kind of many variants. Now, something that I should mention, in all of these examples, the class numbers are the same. The regulars and the class numbers are not different, but that is not, I mean, I think it's not proven that is always the case. It's just in the constructed examples, they always coincide. So here I'm sort of doing sort of a summary of what Perlis has done. And these sort of like, I would say having sort of, I wouldn't like to use the word naive, but in the mathematical sense, the naive way to approach the problem to see what happened with the zeta functions, right? Now, people who work in Galois representations know that this should be, that there should be another way to do it. Like check these functions are functions that come as an L functions of certain Galois representations, right? And of course, for this crowd, this is very, very elementary what I'm going to mention, but in general, so you have this point of view that maybe you could just see what happens with certain other objects and see what happens with the Dedekind zeta function. So the classic old object that probably everyone learns as the first Galois representation or the first favorite Galois representation is the Tate module of an elliptic curve, right? So you have the Tate module of the elliptic curve, you have the L function of that representation, so the L function of the elliptic curve, and of the Elliptic representation, we take an ice prime, and then we have sort of the isogeny theorem will implies that we have these sort of results that the representations are conjugate, the Tate modules are isomorphic for almost all prime P, the coefficients AP of the elliptic curves are the same. This is equivalent to say that the numbers of FP points of the curves are the same and the L functions are the same, right? So we have this sort of classic theorem of Galois representation of elliptic curves. So we would like to see if we have sort of an exact translation to what happened with the Dedekind zeta function. Now, before moving to the zeta functions, we will see that if we have this translation, we will have an improvement, right? Because here we are saying that it is equivalent to see that the pth terms are the same. What we had before in terms of Perlis results and this combinatorial idea, they need to check all the prime powers, not just the powers to the power 1. Okay, so again, so what would be the analog statement? So the analog statement would be, I have to move my screen a little. The analog statement would be, so the zeta function should play the role of the L function of the curve, the representation, the Elliptic representation, you should have sort of corresponding representation of the absolute Galois group that depends on the number field. The Tate module should correspond to some Galois module that also depends on the number field. And the number of FP points on the curve should correspond to the number of FP points on the corresponding curve. And of course, the corresponding curve should be spec OK. Right, so we are trying to guess what we should have. And the theorem that we will get is something of the sort exactly the same as before in the implication of the isogeny theorem. The modules are isomorphic, the P values are the same, the functions are the same, and the number of FP points over specs of the ring of integers are the same. Now, so if you think about this problem, we said, okay, we need to construct a Galois representation that depends on the number field. So what would be the basic Galois representation that comes to the number field? I mean, basically, so the first one that comes to mind, there can only be one, right? It's sort of the first one that you learn as, when you learn Galois theory, the first representation that you learn is the representation of moving the roots of the polynomial, right? Of course, we call roots embeddings and whatever, but we take the number field, we take the set of complex embeddings. That set comes with a natural action of the absolute Galois group. That action is just composition. That gives you a permutation representation, n-dimensional permutation representation by permuting the roots, and by embedding in the natural way Sn and GLNC by the permutation matrices, you have an n-dimensional arcing representation. Now, what is the sort of the associate module to this representation is the free module given by the embeddings, right? So this is that would be the analog to the Tate module. That is the analog, this representation to the Elliptic representation of the Tate module. And so what we need to prove, and that's part of the basic of arting formalism, is that the L function associated to this Galois representation is precisely the zeta function, and that is a fact. The L function associated to this representation is an L function. Therefore, the theorem, which is sort of a classic fact of this is not written anywhere, but this is a fact that everyone should know, is that the distant number fields are arithmetically equivalent if the representations are conjugate, these modules are the same, and for almost all prime, the p terms are the same. This is sort of the improvement in the result of Perlis about this. Now, this result is actually, in terms of the terminology of arithmetic types, it is stated as if you take the arithmetic types and you can count the number of ones in one type, and you count the number of ones in the other type, those two numbers are the same. This is actually a result not of Perlis, but I think one of his students in the 90s, in which they proved that this is the case. Of course, completely different from the approach of Galois representations. There is in a combinatorial way to do so. Now, what is this coming from? Again, so this is the analog things with the zeta function is the L function is this representation, which is the analog to the L function is the L function is this representation, and that the traces of Frobenius are completely determined by the values of APs, right? And this is what, like, I guess you guys call it the Eichler-Shimura relations, right? So the Eichler-Shimura relations for the Elliptic Tate module, it is just that the characteristic polynomial is this nice polynomial over here. For the representation that I just mentioned for the number field, so the Eichler-Shimura relation would be that this is the characteristic polynomial. This is sort of a very nice relation. Now, one thing that is also kind of nice over here that I didn't write in my slides is that from this point of view, one can prove, and that's also a result from 2000s from another student of Perlis, that that if you have the two number fields have the same zeta function, it is equivalent that the number of primes over the number of factors of a little p is equal in both fields. So what I'm saying here is that this G determines the zeta function, and this G of course depends on every p. You don't need to know all the FIs, but as long as you know the G's, you will know the zeta function. That also can be proved very, very easily from the point of view of Galois representations, the point of view that I show you. Now, sort of a summary of all the previous results that we had, or not we, but like Perlis and his co-authors, or people that prove things about arithmetic equivalence, in terms of this representation, can be written in a cohesive way as follows, right? So for example, the degree of representation, it is precisely the degree of the number field. The trace of complex conjugation is the number of real embeddings. The conductor or the arcing conduction of the representation is the absolute value of the discriminant. The Galois closure of the number field, it is the invariant field by the kernel of the representation. So all these first statements that I put in the list of things that sort of we're proving, like each one by separate, all of them can be written in terms of the representation. And I guess this sort of the hardest one, or the most the ones that have the most consequences, which is the group theoretical characterization, can also be written in terms of this Galois representation, and actually give you sort of a little better understanding of what's going on. This thing about the number of conjugacy classes and intersecting with one group another is kind of weird. Like you see it and it works, but you don't have sort of a satisfying explanation as to why. In terms of this representation, the explanation is sort of as follows. So you take, again, any number field contains the Galois closure, okay? That only means that when you do your representation rows of K, you could factorize in this diagram over here, because this contains the kernel, right? This is the restriction function, right? The usual projection function. And then you have this commutativity over here. It turns out that this representation that you get on this group G is precisely the induction of the trivial representation of the group H to the group G, with H is the group determined by the Galois group. Now, knowing this representation, of course, this is a finite dimensional complex representation. This is exactly the same as knowing the character of representation. It turns out that the value of the character here in any conjugacy class is this number over here. Now, that's where the number of conjugacy classes will appear. Now, if you know the number of conjugacy classes, it is not hard to see that you will know the number of these over here, these the character. And if you don't know the character, of course, you know the representation. And if you know these representations, So and this is commute, you know this representation, and if you know the representation, then you know the L function, then you know the zeta function, okay? So that is actually sort of a nice way to observe what happened with the representation over here. Now, a good question would be, okay, but this is just, I mean, it's pretty and everything, but what is new about it? Like we haven't found anything new besides of the things that people have already done, maybe in this combinatorial way. So what I did is I started looking by results about elliptic curves and functions of elliptic curves, and trying to translate those results to this sort of environment of number fields. And one of the results that I found is this following. First, I need to do sort of, I'll give the definition, I'll explain why the definition. So I'll call two number fields weakly arithmetical equivalent if there are two conditions. First, they have the same ramified primes, so the bad primes are the same. And second, for such primes, the p factors of the zeta functions or the local factors of the L functions are the same, okay? So basically here is kind of counterintuitive. What one normally does is, instead of looking for the good things, I'm just focusing in the bad primes, okay? And we said that these two number fields are arithmetical equivalent if these two conditions hold. Now this will give you a lot of freedom in terms of number fields. Freedom in the sense that you could have weakly arithmetical number fields that are Galois, that have fundamental discriminant, or that have degree less than 7. That doesn't happen for arithmetical equivalent number fields, because as explained before, a fundamental discriminant are solitary, degree smaller than equal than 6 are solitary, and if they are Galois extensions, they're also solitary because the Galois closure is determined by the zeta function. So here you have a little more freedom about the fields with this definition. Now, a theorem that I was able to prove, it is the following. If you have two weakly arithmetical equivalent number fields with some other conditions, I'll explain in a second. If these two guys have degree at most 3, or they're Galois of their fundamental discriminant, then the integral trace are equivalent, okay? Now, this seems weird, and I'll explain in a second what is it coming from, but so I'll tell you what is the meaning of this. Now, what is the integral trace of a number field? You take the ring of integers. The ring of integers has a natural bilinear parent on it, which is the trace of xy, right? And then we said that the integral traces are these ring of integers with this bilinear pairing, okay? Now, this theorem basically is the restatement of the following theorem in terms of elliptic curves. Now, you have two elliptic curves that are semi-stable, that have bad ramification of the same primes, and suppose that the local p factors of the L functions are the same. If that happens, then they will have the same local root numbers. Okay, now I need to explain why this is the same. Now, first, there is this word semi-stable. Okay, so I need to translate semi-stability. So I have to came up with semi-stability for number fields. So there are many ways to define, as you know, semi-stability for elliptic curves, but sort of the easiest, the most pedestrian way to do it is a square-free conductor. Now, what is the conductor? Is the conductor of the representation. If I go to the world of number fields, if I see what is the conductor of the representation, I will check that is the discriminant. So semi-stable will translate to number fields. One possible way to say it is that a number fields that have a square-free discriminant, and you can generalize that square-free discriminant a little bit to call it fundamental. Okay, and now that's why this generalization fundamental here. Then I have to put here tame to make things easier. Okay, now I'm asking for they have bad ramification at the same primes and the local factors coincide. That's why I made the definition of being weakly arithmetically equivalent. And what is the consequence? Here, the consequence is that the local root numbers are the same. Now, the local root numbers, when we do the translation to what I was talking about, number fields, they will translate as the Hasse-Minkowski numbers, P numbers of the trace form, when seeing that form as a quadratic form, right? So you have a quadratic form over the rationals, and they have the same quadratic numbers, the same Hasse-Minkowski invariance. Then by the Hasse-Minkowski principle, those quadratic forms are the same. Now, those quadratic forms will be the same as rational forms. You have to do a little more work when we're talking about integral trace forms, because as you know, the Hasse principle doesn't work over quadratic forms over the integers. You have to do a little more work, and that's why I'm here with the condition non-totally real. The non-totally real is to be able to work these results of a spin or genus of quadratic forms and sort of the equality between isometry and spinor genus. Now, what is the connection to make it a little more clear about the trace form and the zeta function? So the connection is as follows. So as I explained, I was inspired by this theorem to talk about trace forms translated from the theorem over here, but I didn't explain to you why do we have this connection with quadratic forms. And the connection is actually very nice. So again, you have your number field and you have the permutation representation. This is the most natural representation you can imagine. Now, what we did before, we said, okay, we have the embedding of Sn in GLN, right? The permutation embedding. But if you think a little bit, the permutation embedding, you can just put it in any, basically almost any group, right? And these groups, you can put it, for example, in the orthogonal group over the algebraic closure of Q, right? The permutation matrices are always orthogonal matrices. Now, then this will give you two maps of cohomology sets. Now here you have the permutation representation, and then you push forward that, and you have this cohomology set here, and this here you live in the world of n-dimensional complex Galois representations, okay? And what I explained before is like, if you take this representation over here, this pi sub k, the one that you get here is that rho sub k, and the artinal function of that rho sub k is the Dedekind zeta function. Now, if instead of looking at that over here, I push forward here on top, then you get to this pointed cohomology set. But this pointed cohomology set, this is a set that parameterizes n-dimensional non-degenerate quadratic forms over Q. It turns out that, I mean, if you start with the most natural permutation representation of your number field, here you should have the most natural quadratic form of your number field. Now you have to do a little work that actually is the rational form given by the trace form, not over the ring of integers, but over the full number field. And now the connection between these two guys, the connection that I made before with Rolle's theorem, is that the root numbers of a representation here are connected by the Hasse-Minkowski numbers of the trace form over here. That's due to a theorem of Serre's and I guess Delin, which make the connection. Therefore, you can jump from here. The zeta function will determine the rational quadratic form, the rational trace form, and you have to do a little work to be able to see that the L function will determine the integral quadratic form in certain conditions. Now, why I'm obsessing over the integral quadratic form and not over the rational quadratic form? The rational quadratic form doesn't give you much information about the number field. So for example, if you take any two cubic fields that are Galois, they don't need to have even the same discriminant or whatever. The rational quadratic form given by the trace form is always the same. It's the form 1, 1, 1, okay? But the integral quadratic form actually determines a lot of the quantities of the number field. For example, the discriminant, okay? But the rational is not. So it's important to focus what happened with the integral form and not the rational form. Okay, so those are the results of a couple of years ago. Now, more recently, I started thinking about, okay, so what about the original theorems about the arithmetic types? So what Perley's proof is that, so I'll just say it in probabilistic terms. Two number fields have the same zeta function if the probability of having the same arithmetic type is always 1, right? If you want to see if two number fields have the same zeta function, you have all the arithmetic types, and you count how many of those are the same, and you have to count with probability 1, and then they will determine the function. That's a little too much effort. So a natural question is, can we actually improve that? Can we just take the probability from 1 to a smaller number? So for example, can we say that maybe if the probability is bigger than a certain constant, that of course will depend on the field, could we say that the number fields are arithmetically equivalent? And then just playing with some heuristics and with some Chebotarev sets and some splitting sets, I was able to prove that the following theorem: two number fields have the same zeta function if the set of primes that have the arithmetic type, the probability is bigger than 1 minus 1 over n squared. That number over there. Okay, so you don't have to go to probability 1, you just have to go to probability 1 minus 1 over n squared. Okay, and actually, when I was doing my heuristics, but the number that I wanted to prove was actually this one. This is the one that I start trying to prove, because what I had found, but I wasn't able to get to this number. The one that I was able to go was this number over here. And of course, my heuristic is very humble here. I can prove it for degrees 2 and 3, which the conjecture is true, and sort of by computational sort of evidence for degree 4, I think also, this is also true for 4, modulus on laziness on my part, that you have to just check certain Galois groups of degree 4. So that's one way of improvement. And again, this also goes through the path of Galois representations and sort of the analogous statement with counting points on elliptic curves, and that's sort of a nice result. And a little sort of more effective result, I would call it, is, and there are a bunch of numbers. I don't like to put slides with a bunch of numbers, but sort of, if you have two number fields and you want to see when they have the same zeta function, and let's say you want to, this is a very strong computer, and you want to say, I just only want to check finally many primes, right? I only want to check the arithmetic types for only finally many primes. It turns out you can do it. This is sort of the restatement of one version of the isogeny theorem. And the point is that one necessary condition that you have to put is that the two number fields have the same Galois closure, and that is not that crazy because, again, we know that number fields with the same zeta function will have the same Galois closure. It turns out that if you check up to x sub k many primes that the arithmetic types are the same, then the zeta functions are the same. Now, what is this x sub k? It is a bound that depends on the determinant of the Galois closure, that is d to the power 310. And this is basically just using effective Chebotarev density theorem bounds found by Asif Zaman and some more people recently. And those are the bounds that you have to check. These are, again, effective Chebotarev under GRH. But anyhow, so the whole point over here is, again, using this sort of method of Galois representations, very sort of elementary Galois representation, you can improve on many of the results of previous people. Here, I think one improvement that one can dance, but I haven't been, I have to work on it a little bit, is that instead of having the bounds in terms of the Galois closure, you could have probably the bounds in terms of the actually discriminant of the number field. I mean, might be a little uglier than the ones that we have over here, but that's that would be a better point. I think that's all I had for you guys. I hope my time is okay.
Oh, thanks. Thanks for your talk. Do someone have some questions, some comments maybe you want to share with us?
In the previous result, the n was the degree of your field, right?
Yes, in here is that you have number fields of Dn, and then you have this bound over
here. So it has nothing to do with the Galois closure. It's just the degree of the field.
No, this is sort of a statement of like when you have, let's say you have two sort of very nice schemes over Z, and you want to count the number of points of these two guys over here. If the number of FP points are the same, how can you tell about the sort of the L functions of the Jacobians or something like this? You count this. This is basically a result about the calculate the dimensions of complex cohomology of certain schemes related to the fields.
Let me ask you a question on this last slide. So this last result that you stated it looks like this sort of like Hecke bound for modular forms, right? You have like two modular forms, and then you check whether the APs are the same, and you have a bound such that if you reach this bound, the two forms are exactly the same if they lie in some particular space. But then you have a second version using congruencies, and I don't know whether this has some interest in for number fields, whether the zeta functions are congruent mod P or something like this, and whether you also have information which also translate into congruencies on the Galois representations, right? So I don't know whether this has been studied or does it make any sense or not.
I'm not sure. There's this, what is like the, I forgot exactly the name, but there's for the general L functions, you want to count how many primes you have to count to see if the L functions are the same, and then you have to do some sort of congruences. And I think these are examples in the function that you could just have it, but in these bounds with Chebotarev are actually better than the bounds that you usually found for general L functions, because these functions are very convenient in the sense that they have, like the Satake parameters of these functions are all like very easy to calculate, and like the bounds are kind of small. So So I don't know, but I have to check it out to see if they will improve.
Okay.
Any questions? Any comments?
In your conjecture, how you led to that density? Is that by looking at the Artin representations? How you get 1 minus 2 over n squared?
No, I was counting this very combinatorial here. I was counting sort of the splitting primes. I start what would happen if the number of fields were Galois, and then I was kind of comparing sort of how the splitting behavior will work in both fields, and I will sort of found this sort of bounds, but honestly, it was not. So the sort of how I started is not related to Galois representation. It was more about how splitting primes behave in one of the fields and in their Galois closures. Actually, it was not. And then that's how I moved then. And so here it was. I start with this bound. I knew it was like 1 minus something I want to prove, and then I have to move in a different direction for this. So my heuristics are sort of unrelated to Galois representations. Someone sent something in the chat. Oh, I see.
Some other question maybe or comments? Okay, if not, let's thank again the speaker, please.